Welcome to the Deep Dive, where we take your complex topics and distill them into essential, actionable knowledge. Today, we're plunging into something absolutely foundational for modern business resilience: remote replication technologies.
Hmm.
Think about it. In our always on, always connected world, if information is power, then ensuring that power is always available, even across vast distances, is not just important, it's a paramount. Imagine a huge global company, right? Processing millions of transactions every hour, customers everywhere. For them, even a tiny bit of downtime or losing just one order, it's not just an inconvenience, it's potentially catastrophic, financially, reputationally, everything.
Precisely. Yeah, for companies like that, continuous access to information is completely non-negotiable. The consequences of data unavailability, even for a short while, they can be staggering. We're talking potentially millions of dollars per hour in some industries. So this deep dive, we're going to illuminate the intricate strategies and the advanced tech that organizations use to maintain that uninterrupted flow, especially when facing a disaster at their main site. We're basically looking at how they weave this sophisticated digital safety net, cast far from home, to catch their most valuable asset, their data.
Okay, so what's our mission today then? We're going to unpack the different modes of remote replication, sort of the fundamental approaches. We'll dive into the various technologies that actually make it possible, explore some of these complex multi-site setups, and even see how this all works in the world of virtualization, which is, everywhere now. It's a fair bit to cover, but by the end, you'll have a really clear understanding of what's happening behind the scenes. The stuff that keeps your favorite online services running no matter what.
That's right. We'll explore the core principles, the rules that govern how data gets duplicated across geographical divides, and importantly, the nuanced trade-offs involved. Achieving different levels of data protection versus recovery speed. We'll be tackling key questions like, how do companies really ensure zero data loss when disaster strikes? What does it actually mean for data to be buffered across a network? And why does that matter so much for your applications? How do they protect against more than just one site failing? Let's unpack this. It's pretty crucial stuff.
Okay, so when we talk about remote replication, you mentioned it kind of boils down to two main approaches, synchronous and asynchronous. For someone maybe new to this, what's the core distinction? Why is this difference so critical?
Yeah, at its heart, the real distinction lies in when that write complete acknowledgement is sent back to the application. It's all about the timing of that signal saying, okay, your data is safe.
Mm. Let's start with synchronous. Synchronous remote replication. This one is, well, it's the stricter of the two. Designed for the absolute highest level of data protection. With synchronous, when a host application initiates a write, say a customer places an order or a bank records a trade, that write must be fully committed, like safely recorded, to both the source storage system at the primary site and the remote target storage system at the DR site before the source system sends any acknowledgement back to the production host saying, yep, write complete.
Whoa, okay. So the application literally has to wait for a confirmation signal from two different places, potentially miles apart. That sounds like the gold standard for data safety, definitely.
Whoa.
But there must be a catch, right? Waiting for that double confirmation across a network?
Mm-hmm.
That's got to slow things down. You're absolutely spot on. That waiting period. That's precisely the catch. It's the big trade-off because the application has to pause, essentially, and wait for that round-trip confirmation from two distinct locations. Synchronous replication can, and often does, introduce a noticeable delay, a latency hit. It effectively stretches the transaction time across the network distance for every single write. And this is where, the laws of physics, specifically the speed of light, become a very real bottleneck. The round-trip time for the data and the acknowledgement back, it significantly impacts performance. So because of that, synchronous replication is typically deployed over shorter distances. We're usually talking tens of kilometers, maybe up to 100 or so in some cases, to keep that latency impact manageable. Try stretching it across continents. The performance hit usually becomes just, well, unacceptable for most applications.
Okay, that makes sense. It's a physical limit. Now, what about failures? What happens if the network link between those two synchronous sites goes down? Does everything just grind to a halt?
That's a really important point. If the network links connecting the primary and remote synchronous sites fail, the replication itself, it's immediately suspended. But this is key. The production work on the source storage array can continue uninterrupted. The applications keep running. The array's operating environment, its software, is smart enough to meticulously track all the writes that haven't been transmitted yet. It buffers them, essentially queues them up locally, waiting for that network link to come back online.
So it holds on to those changes at the source. But the danger then is, what if the source site itself fails before that link comes back up and those buffered changes get sent?
Exactly. That is the critical risk window. If the network link is down, and then the source site fails catastrophically before those buffered writes can be transmitted, some data will be lost at the remote site. In that specific sort of cascading failure scenario, the recovery point objective, the RPO, it's no longer zero. Those untransmitted buffered writes, they're gone. Now, to try and minimize the typical impact on application response time, make synchronous a bit more usable over those shorter distances. Modern storage arrays are pretty clever. They initially place the writes onto the cache of both the source and target arrays. Think of cache as like super fast temporary memory. The actual writing of this data down to the slower physical disks, what we call destaging, that happens a bit later, kind of in the background. This two-stage caching helps absorb some of that immediate latency, making synchronous a more viable option without totally crippling performance, at least over those manageable distances.
Okay, that paints a very clear picture of synchronous. Absolute data fidelity, 0 RPO. But with those performance and distance strings attached. So what if an organization needs to replicate data across oceans? Or maybe they have applications that just cannot tolerate any added latency, not even a tiny bit. That's where asynchronous remote replication comes in, right? How does it differ fundamentally? How does it tackle those challenges?
Yep, you've led right into it. Asynchronous replication takes a fundamentally different tack. It prioritizes application performance and long-distance capability over that immediate, absolute data synchronization. You can think of it as the write first, send later approach. Here's how it works. A write operation comes in, it gets committed to the source storage system, and critically, it's immediately acknowledged back to the host application. Got it. Done. The data is then buffered at the source, held temporarily, and transmitted to the remote site later. Maybe in batches, maybe continuously as network bandwidth allows, but it's not holding up the app.
Right, so that definitely sounds much faster for the application itself. Right. But if there's a delay between the source committing the data and the remote site actually getting it, doesn't that inherently mean potential data loss if the source fails during that gap?
Precisely. That is the core trade-off with asynchronous. Because there's that lag, that delay between the write being committed locally and it being fully replicated remotely. The data at the remote site will always be slightly behind the source. Could be seconds, could be minutes. This results in what we call a finite, non-zero recovery point objective, RPO greater than 0, which means, yes, some data loss could occur if the source site fails before that buffer data gets fully transmitted and secured at the remote site. The exact amount of potential data loss, that RPO value, depends on a few things. The size of the buffer at the source is one. How much data can it hold before it has to send it? Also, the available network bandwidth. How fast can it drain that buffer? And of course, the write workload itself. How quickly is the application generating new data? Heavier workload, tighter bandwidth. You might see a larger buffer buildup and potentially a higher RPO. Maybe minutes, maybe even in some cases an hour or more.
Okay. But the big plus is performance and distance then.
Exactly. The immediate acknowledgement back to the host means there's virtually no noticeable impact on the application's response time. It feels fast. This makes asynchronous really well suited for performance-sensitive apps. Think web servers, big data analytics, lots of internal enterprise stuff where they can tolerate a small, defined amount of potential data loss. And crucially, this mode really shines for long distances, hundreds, even thousands of kilometers. Why? Because that network latency, the time it takes signals to travel, it doesn't directly hold up the host application for each write. For a global company replicating data across continents, asynchronous is often the only practical way to do it for many services.
And I think I recall something about locality of reference with asynchronous. That sounds like a clever way to save bandwidth over those long, potentially expensive network links. What's that about?
Yes. Locality of reference. It's a really neat and very practical optimization that asynchronous replication can do. Imagine an e-commerce system updating an order status multiple times very quickly, like processing, then packed, then shipped, all within maybe a few seconds. If the same data location, the same block on the disk, gets written multiple times while it's still sitting in the source buffer before it gets transmitted, asynchronous replication is smart enough to recognize this. It realizes, hey, only the final version of that data block actually needs to be sent across the network. All those intermediate writes, the processing and packed ones in our example, they're essentially eliminated from the transmission queue. This feature can significantly conserve network bandwidth, especially with certain types of workloads, by avoiding sending redundant data over long distances. That means cost savings and better efficiency.
Okay, so let me try and summarize this for the listener. Synchronous gives us that ironclad zero data loss guarantee, that zero RPO, but it comes at a cost. The potential performance impact, and it's limited by distance, really for the absolute mission-critical stuff where you cannot lose a single bit. Asynchronous, on the other hand, trades off that absolute zero RPO. You accept a small potential data loss window, but in return, you get much better application performance, especially over long distances, because it buffers the data and sends it later. What really stands out to you about how these two fundamental modes address such different business needs and, I guess, risk appetites?
Yeah, what stands out most is how clearly they illustrate that fundamental dilemma in disaster recovery planning. It's always a balancing act. Synchronous is for the crown jewels. The never lose a single transaction no matter what data. Think core financial ledgers, real-time trading systems, maybe critical patient records. The cost of losing even one piece of data there is just astronomical, so it outweighs a performance penalty or distance limits. The business need dictates the tech. Asynchronous. That's for data that's still really important, don't get me wrong, customer databases, product catalogs, maybe analytics data, but where continuous high-performance operation is also critical, and we're losing maybe a few minutes or even an hour of data in a major disaster is an acceptable risk, especially if it means keeping the primary application lightning fast and available worldwide. The choice isn't about which one is inherently better. It's about which is the right fit, appropriate, and cost-effective for a specific application's defined RPO and RTO needs. It's a strategic business decision, really, not just a technical one.
Got it. Okay, so beyond just the timing sync versus async, you mentioned the actual mechanics, like how the data gets replicated can vary too, based on where the replication smarts actually live.
Exactly. The intelligence, the software doing the work can reside in different places. On the host server itself, within the storage arrays, or even within the network fabric. Each location brings its own set of pros and cons.
We often hear about host-based stuff for local tasks, like managing volumes or snapshots on a server. How does host-based fit into the remote replication picture? Is that common for enterprise DR?
That's a good question. Host-based remote replication does exist. It typically involves software agents running directly on the servers, managing the replication process. But generally speaking, it's less common as the primary remote replication strategy for large enterprises. Why? Well, a few reasons. First, it consumes server resources, CPU cycles, memory which could otherwise be used by the applications themselves, so it can impact performance. Second, management can get really complex really quickly. Imagine configuring and monitoring agents on hundreds, maybe thousands of servers individually. It doesn't scale easily. And often, host-based solutions might not integrate as tightly with the underlying storage features as array-based methods do. So while you might see it for very specific application-level needs, or maybe in smaller setups, the industry trend for robust, large-scale remote replication definitely leans towards array-based or network-based solutions. Our source material reflects that focus too.
Okay, that makes sense. Let's dive into array-based replication then. This sounds like it pushes the work onto the storage system itself, freeing up the servers.
It's exactly right. With array-based remote replication, the intelligence, the replication engine, is built right into the storage array's operating system. This is a big plus because it offloads the host servers completely from those replication tasks, lets them focus on running the actual business applications. We've already touched on synchronous array replication, right? Both source and target arrays confirm the write before the host gets the OK. Zero RPO, optimized with cache. And we copy that key risk. If the network link fails, replication pauses, the array tracks changes locally. But if the source then fails during that outage, potential data loss, that RPO is no longer zero in that specific window.
Right. But you also mentioned another array-based type, disk buffered. You called it a hybrid.
Yes. Disk buffered replication. It's a really interesting approach within the array-based category. You can think of it as a clever hybrid, and it tries to find a middle ground, balancing the strict RPO and consistency you get with synchronous, with the distance flexibility and bandwidth efficiency you often find in asynchronous methods.
A hybrid trying for the best of both. That sounds potentially very useful. How does it actually manage that balancing act?
It operates on a very precise cyclical basis. Let's imagine an organization needs to replicate, say, large analytical data sets across the country. Synchronous is too slow and maybe too expensive over that distance, but they still need a high degree of consistency for their reports, maybe more than typical asynchronous offers. Here's how disk buffered works. At the start of a cycle, the network links between the source and target arrays are temporarily suspended, just for a short, predefined time. No data flows across the network. While the production application keeps running on the source, the array creates a consistent point in time or a PIT local replica of the source device, like taking a perfect instantaneous snapshot locally. This ensures the data being prepared for transmission is internally consistent.
Okay, so it pauses the network, takes a clean snapshot locally, then what?
Then, once that local PIT replica is ready and consistent, the network links are re-enabled. And the data from that local replica on the source array is transmitted efficiently across the network to its corresponding remote replica on the target array. Optionally, once that pair is synchronized, you can even create another local PIT replica on the remote device at the target array, giving you an extra consistent recovery point over there. After the transmission finishes for that cycle, the network link is suspended again, and the whole process repeats. Take another local snapshot, transmit it, suspend, repeat. The frequency of this cycle, how often it happens, depends heavily on the available network bandwidth and, importantly, the rate of data change on the source. Lots of changes. You'll need more frequent cycles.
Ah, okay, so it's like a very disciplined batch process. Gather changes, take a perfect snapshot, send that consistent snapshot, then get ready for the next batch. And you mentioned something about incremental resync. That sounds like a big bandwidth saver.
Precisely. That batch or cycle approach is key. And yes, a huge benefit of disk buffered is that because it uses those consistent point-in-time local copies, it can meticulously track the changes between consecutive snapshots. This allows for incremental resynchronization. Instead of sending all the data every time, it only needs to transmit the blocks that have actually changed since the last successful snapshot was sent. This dramatically reduces the amount of data hitting the network link each cycle. So compared to pure synchronous and even some continuous asynchronous methods, disk buffer typically requires less bandwidth. That makes it really attractive for long distances or where network pipes are constrained or expensive. Now, the RPO here won't be zero, of course. It'll be tied to the frequency of those cycles, maybe minutes, maybe hours. But you get a very consistent remote copy at that RPO.
Got it. Consistent but not instantaneous. A different kind of trade-off. Okay, what about the third category, network-based replication? You mentioned CDP continuous data protection. How does that work if the intelligence isn't on the host or the array?
Right. With network-based replication, the replication smarts live in the network path itself. Typically, this involves dedicated appliances, physical or virtual, that sit strategically between the hosts and the storage arrays. The network itself becomes the intelligent hub for replication. CDP is a prime example of this approach.
So the replication happens kind of midstream. That sounds like it could be incredibly flexible, especially for organizations with a mix of different servers and storage systems, right? It doesn't care what's on either end.
That's one of its biggest strengths, absolutely. Network-based replication, especially CDP, is known for its ability to work seamlessly across a wide variety of server platforms and storage arrays, highly heterogeneous environments. It's ideal if you have gear from different vendors. It centralizes the replication function and offloads the burden from individual servers and arrays, which can really simplify management. Now, the mechanics of CDP are quite interesting, and this is where its power comes from. It starts, like most replication, with an initial synchronization to get the remote replica baseline established. Once that's done and continuous replication kicks in, all new write operations from the host heading towards the source storage get split. The appliance intercepts and splits the write.
Splits it into two copies. Where do they both go?
Good question. One copy of the write is sent to a local CDP appliance at the source site. This appliance is sort of the brains of the operation locally. The other copy goes straight through to the production volume on the source storage array, so the application's write completes quickly on the primary storage. Now, after that local CDP appliance receives its copy of the write, it does some magic. It forwards that data, usually tagged with a very precise timestamp, over the network to the corresponding CDP appliance at the remote site. And the remote appliance, when it gets the data, doesn't immediately write it to the main remote replica volume. Instead, it writes it sequentially into a dedicated journal volume. This journal is the absolute key to CDP's unique capability.
A journal.
Yeah.
Like a log of every single change.
Exactly like that. A highly granular log. Now, for asynchronous CDP operation, which is common for long distances, the writes might be accumulated briefly at the source CDP appliance first, and crucially, this is where more intelligence comes in. Redundant blocks can be eliminated right there in the buffer. So if the application writes the same block multiple times quickly, the CDP appliance can be smart enough to only send the last version across the network. Another big bandwidth saver, similar to that locality of reference idea. The unique writes that do need to be sent are then sequenced correctly using those timestamps, often compressed. A checksum is calculated for integrity, and then they're transmitted efficiently over the network. Could be IP, could be fiber channel to the remote CDP appliance.
Wow, so it's optimizing, compressing, timestamping everything. It sounds like a super detailed digital video recorder for your data. You can rewind to almost any specific moment.
That's a fantastic analogy. It really is like that. When the remote appliance receives the data, it verifies the checksum, uncompresses it, and writes it into that remote journal volume, timestamp and all. Finally, data is moved from that journal volume onto the actual remote replica volume at certain intervals or based on policies. But because every write is captured in that journal with its precise timestamp, CDP allows for recovery to any specific point in time recorded in the journal, not just the time of the last snapshot or the last batch. Imagine getting hit by ransomware, or maybe a user accidentally deletes a critical database table. Instead of rolling back to a backup from hours ago, CDP potentially lets you rewind the data state to the exact second before the corruption happened. It offers incredibly granular RPOs, often down to seconds. It's a game changer for recovery precision.
That level of granularity is incredible. Okay, so we've seen two-site setups with sync, async, disk-buffered CDP. But sometimes that's still not enough, right? You mentioned three-site replication.
That's right. For organizations with the absolute highest resilience requirements or very specific RPO needs across multiple failure domains, a simple two-site DR strategy might not cut it. This is where three-site remote replication architectures come in. They create these complex, multi-layered protection schemes. It's about designing for broader, more catastrophic disasters.
And this often involves a bunker site, doesn't it? Like an intermediate, often highly secure data center. Tell us how these multi-hop setups work. Why go to that extra complexity?
Exactly. The bunker site, that's the common term, acts as an intermediate storage array. It's usually geographically separated from the primary site, but maybe not as far away as the final DR site. Data flows from the primary source to this bunker in the first hop. Then, from the bunker, it flows to the final, often much more distant remote site in the second hop. This multi-hop design provides significantly enhanced protection against major disasters that might affect both the primary site and a nearby secondary site. Think large-scale regional events. There are two main ways this is implemented, and they offer different RPO characteristics for that final remote site.
Okay, what are the two main flavors?
The first is often called synchronous plus disk buffered. In the crucial first hop from the source to the bunker, you use synchronous replication. This is absolutely key because it guarantees zero data loss between your live production environment and that bunker site. The bunker is always perfectly up to date. Then for the second hop, from the bunker to the final remote site, a consistent point in time, or PIT, local replica is created at the bunker. Data is then transmitted from that local replica at the bunker to the remote replica at the final site using the disk-buffered approach we talked about earlier, setting consistent snapshots and cycles.
Okay, so the bunker gets the real-time zero RPO feed.
And then the bunker sends consistent but slightly delayed snapshots further down the line to the ultimate DR site. That's it precisely. This method typically needs at least 4 storage volumes: source, bunker replica, bunker local PIT for sending, and the final remote replica. And because that second hop uses disk buffering, the RPO at the final remote site is usually in the order of hours, depending on the cycle frequency. It's a deliberate trade-off: immediate zero-loss protection nearby and consistent bandwidth-efficient protection further away. Great for an ultimate fallback site that doesn't need instantaneous data.
Okay, what's the second three-site approach?
The second main method is synchronous plus asynchronous. Again, that critical first hop, source to bunker, is synchronous. Zero data loss guaranteed between production and the bunker. Immediate failover capability right there. What changes is the second hop. Here, the replica volume at the bunker site acts as the source for standard asynchronous replication to the final remote site. So, data arriving synchronously at the bunker is then buffered and streamed asynchronously to the distant site.
Right, so this would give a much tighter recovery window for that final remote site compared to the disk-buffered second hop, wouldn't it? Because it's sending data more continuously.
It absolutely does. This method usually needs a minimum of 3 volumes: source, bunker replica, and final remote replica, one less than the sync plus disk buffered way. And because that second hop is asynchronous, the RPO at the final remote site is typically much lower, often in the order of minutes. It offers a much quicker recovery point at the distant location.
Makes sense. Now, the real value here is in handling complex failures, right? How does it play out if, say, the bunker site itself goes down?
Exactly. That's where the 3-site strategy really proves its worth. Let's run through scenarios.
Scenario 1. Disaster hits the primary source site. No problem. You fail over to the bunker site with 0 or near 0. Data loss thanks to that synchronous first hop. Business continues from the bunker. Scenario 2. The bunker site itself fails, or the network link between the source and the bunker fails. What happens? Well, the source site keeps running production normally, but obviously replication to the bunker stops. And consequently, updates also stop flowing to the final remote site. So the remote site's data starts getting stale. However, and this is a crucial advantage, if the source site then also fails while the bunker is still down or disconnected, you still have an option. You can fail over operations to that distant remote site. The RPO there will depend on how long it's been since the bunker link failed, but you have a recovery point. You're not completely out of options, even with 2 points of failure. That's huge for ultimate resilience.
Wow. Okay, these 3-site architectures are clearly serious business. For the most demanding situations where you need that 0 RPO first hop, but also need protection against wider failures, maybe even needing to recover across the globe, it's like strategic data placement on a whole other level.
It absolutely is. Significant planning, engineering, and investment go into these. But, remote replication isn't just about disaster recovery and protecting against failures. It's also a really fundamental tool for large-scale data migration.
Ah, right. Moving data between systems or data centers, not just for safety, but as part of infrastructure upgrades or consolidations.
Exactly. Think about needing to move terabytes or even petabytes of data to a new storage array, or maybe migrating an entire application suite to a different data center. Remote replication technologies often underpin these moves. This typically involves what we call push or pull operations.
Push or pull, what's the difference there? And you mentioned hot versus cold operations too. How does that fit in?
Right. So a push operation is where the source system actively sends or pushes data to the target system. The source is in control. A pull operation is the reverse. The target system actively requests or pulls data from the source. The target is in control. Whichever way you do it, a key mechanism often used is something called the protection bitmap. Think of it like a checklist or a map for the data being moved. Each bit in this map represents a chunk of data on the control device. That's the source for a push or the target for a pull. When the migration starts, usually all the bits are set to 1, meaning this chunk needs to be copied. As each chunk is successfully copied and verified, its corresponding bit gets flipped to 0, meaning this chunk is done. It's a way to track progress meticulously.
Okay, like a progress bar at a very granular level.
Pretty much, yeah. Now, during these push-pull migrations, there's a critical rule often enforced for data integrity. Host access to the remote device, the one not currently acting as the control device, is generally not allowed. Why? Because the array controlling the migration doesn't have full insight or control over external changes happening on that other array simultaneously. Allowing writes there during the migration could mess things up, lead to inconsistencies. It's a safety lock.
Got it. Protects the integrity of the move. Now, what about hot versus cold?
Right, hot versus cold applies to the control device during the migration. A cold operation is the simpler, safer approach. The control device source for push, target for pull is taken offline, made inaccessible to host applications for the entire duration of the migration. You basically stop the application, move the data, then restart the application on the new system.
So downtime is required. Schedule it for a weekend maintenance window kind of thing.
Exactly. It's a take down, copy, bring up method. The big benefit, it absolutely guarantees data consistency. Since nothing is changing on the control device while it's being copied, you know the migrated copy will be perfect. Stays this way, but requires that outage window. In contrast, a hot operation is designed to minimize or eliminate that downtime. It allows the control device to remain online and accessible to host applications during the replication process. Obviously, this is much preferred for critical applications that need to run 234/7. During a hot migration, applications can still write new data or change existing data on the control device while the background copy is happening. The magic here is that the control array has to be intelligent enough to track all these ongoing changes. It uses mechanisms, maybe linked to that bitmap or other, change tracking logs to make sure that any data modified during the migration process is also captured and eventually synchronized to the target device.
So cold is simple and guarantees consistency but needs downtime. Hot keeps the application running but needs much smarter technology underneath to track all the mid-flight changes and ensure everything ends up consistent on the other side. Sounds like a complex dance.
It is indeed a complex orchestration, yeah. But for many businesses, especially global ones needing continuous operation, hot migrating capabilities are absolutely essential for things like tech refreshes or data center moves without disrupting the business.
Okay, this naturally leads us into virtualization. Because everything seems to be virtualized these days. How does remote replication and migration work in these environments?
That's a great transition because virtualization has profoundly changed the game here too. It's not just about replicating the underlying data volumes anymore. In virtualized environments, we could replicate the virtual volumes holding the VM files, yes. But we also gained this incredibly powerful ability to perform full virtual machine migration across sites, moving the entire running VM.
So not just the data, but the whole compute instance, OS, apps, memory state, moving across the network, maybe even across the world. That seems almost like science fiction.
It can feel that way.
Yeah.
And it's incredibly powerful. So at the base level, yes, you replicate the virtual volumes using the methods we've discussed, synchronous, asynchronous, CDP, etc. That protects the VM's disk files. But VM migration goes further. It allows moving entire running virtual machines from one physical host server to another, often without even powering them off. Think live migration. This is huge for business continuity, moving VMs off a failing server. Or for planned maintenance, take a server down without impacting the services running on its VMs. And it's also fantastic for load balancing within a data center. Move busy VMs to less loaded servers dynamically.
Okay, so how is that live migration actually done? Are there different ways?
There are two main techniques to understand. The first is hypervisor to hypervisor VM migration. Think VMware vMotion, Hyper-V live migration. This technique primarily involves moving the active state of the VM. What does that mean? Mostly, it's copying the contents of the VM's memory, its live RAM, from the source hypervisor server to the target hypervisor server. Once the memory is copied and synchronized, control of the VM disk files is then transferred to the target hypervisor. Now, here's the critical requirement and a limitation. Both the source and target hypervisors must have access to the same shared storage where the VM's virtual disks actually live. The virtual disks themselves, the big files, are not moved during this process. Only the live memory state and the pointer saying your disks are over here get transferred. So this is great for moving VMs around within a single data center or between closely connected data centers that share storage.
Okay, so it's moving the running part, but the storage stays put and needs to be accessible by both ends. What if you need to move the storage too, like to a completely different data center with different storage?
That's where the second technique comes in, array-to-array VM migration. This is much more comprehensive migration. It moves the entire VM, its configuration files, its logs, its swap files, and crucially, its virtual disk files from a source storage array to a target storage array, which could be remote. A huge advantage here is the ability to move VMs across dissimilar storage arrays. They don't have to be the same make or model. This offers tremendous flexibility for things like migrating to new hardware, moving to the cloud, or setting up DR sites with different storage infrastructure.
Ah, so this is how you truly move the entire digital footprint, storage and all, to a new home. How does that process work?
It typically starts by copying the VM's metadata, the configuration file settings, etc., from the source array to the target array. Sets up the blueprint. Then, the big part, the actual VM disk file, the virtual hard drive, is replicated to the new location. This can take time, depending on the size and the network. Now, similar to hot data migration, during this disk replication, the source VM might still be running and changing data. So it's absolutely essential to track these ongoing changes on the source. The array or replication software monitors these changes. Once the initial bulk copy of the disk file is complete, a final synchronization phase happens. Any blocks that changed on the source since the replication started are then replicated to the target, bringing the target copy fully up to date. This final sync is usually very quick, often allowing the VM migration to complete with minimal or sometimes even zero perceived downtime for the application running inside the VM. The benefits: better performance of moving to faster storage, better capacity balancing, and true infrastructure independence for VM placement and recovery.
Got it. So array to array gives you that complete portability across different storage, moving the whole enchilada. It really seems like the constant theme here across all these technologies is that perpetual balancing act. Consistency versus performance versus network cost versus recovery time.
You've nailed it. That is the recurring challenge and the core set of trade-offs in absolutely every remote replication and migration scenario. RPO, RTO, performance impact, bandwidth consumption, cost. It's the multi-dimensional puzzle every organization has to solve based on their specific needs, budget, and tolerance for risk.
Well, we have certainly navigated a complex landscape today. We started with the fundamentals: synchronous for zero data loss but distance limited, asynchronous for performance over distance with a slight RPO trade-off. We looked at array-based methods like disk buffered for consistent snapshots and network-based CDP for that incredible point-in-time granularity. We explored the resilience of three-site architectures with bunker sites for handling major regional disasters. And we saw how replication enables not just DR, but also data migration with hot and cold options. Finally, we dove into the virtual world, understanding how VMs can be migrated live, either just their state or their entire footprint, including storage. It's truly clear these technologies are the kind of the unsung heroes keeping our digital world spinning.
Absolutely. The ability to meticulously copy data and even entire live computing environments across potentially vast distances, it's utterly fundamental to minimizing disruption, minimizing data loss in the face of, well, the inevitable glitches, failures, and disasters. We've seen how the different modes sync, async, disk buffered, CDP cater to really different RPO and RTO demands, and how array-based and network-based solutions provide these robust, flexible ways to implement them. These aren't just abstract concepts, they're the strategic bedrock of digital resilience for almost everyone.
And those three-site setups, they really hammered home the lengths organizations will go to, the complexity they'll embrace to ensure their most vital information is safe, not just from a single fire or flood, but from potentially cascading large-scale failures.
Right. And the evolution into virtualization with live VM migration across servers and even across different storage systems, that just pushes the boundaries of resilience and operational flexibility even further. It's about ensuring not just that the data is available, but that the application is available quickly, regardless of what's happening to the underlying hardware. It's quite remarkable, really.
So what does this all mean for you, our listener? Well, understanding these mechanisms isn't just for the IT crowd. It's really about appreciating this incredibly intricate, hidden ballet of technology. It's what allows our digital lives, our banking, our shopping, our work, our entertainment to remain largely uninterrupted, even when things go wrong somewhere. It's the invisible safety net beneath almost everything we do online.
Indeed. And thinking ahead, given the relentless growth in data volumes, the increasing reliance on continuous digital services, the rise of AI demanding constant data access, and the global nature of business, it really raises a crucial question. As this digital dependency deepens and data explodes, how will these remote replication and migration technologies continue to evolve? How can they deliver near instantaneous global availability and recovery without completely overwhelming our network infrastructure or breaking the bank? Finding that next iteration of the balance we've discussed, that's the ongoing challenge, and it's what will keep driving innovation in this absolutely vital field.